evening and good morning, everyone. I'm Jingfeng, a researcher from Recon AIP. Today, I'm going to host the TrustML Young Scientist Seminar. Before that, allow me to briefly introduce Recon AIP to our valuable guest. The full name of Recon AIP is Recon Center for Advanced Intelligence Project. AIP was founded in 2016 as the Research Center for the MAX AIP project. AIP Center conduct Japan's leading AI research, which is headed by Professor Sugiyama. AIP aim to enhance AI fundamental technology and its real-world applications. We encourage the collaboration with various researchers and engineers in related fields. We would be grateful if you could visit us in our Nihonbashi office in Tokyo in near future. Next, I'm going to introduce our today's speaker, Guaran. Guaran is a second-year PhD student in computer science department at University of Maryland, College Park. He received his bachelor and master degree in mathematics at IIS, the best institute in India. His research focused on understanding the phenomenon of adversarial examples and robust generalizations in neural networks, and on building robust machine learning system for a low computational budget. Let's welcome Guaran to give today's talk towards efficient evaluation and training of adversarially robust neural networks. Welcome.
Yeah, I wanted to thank the Recon AI Center for inviting me to give this talk. And I'm very happy to speak here about my research. Welcome to my talk on titled Towards Efficient Evaluation and Training of Adversarially Robust Neural Networks. I'm currently a second-year PhD student in the University of Maryland, College Park, in computer science. And previously, I did my BS and MS in mathematics at the Indian Institute of Science in Bangalore. And I'll cover some of the research which I've done in this field. So first, I'll give a very brief introduction of the field of adversarial robustness. So it's well known that deep neural networks have outperformed the best of classical methods in many fields like computer vision and natural language processing at this point. While these networks achieve near human accuracy on many benchmark data sets, they're still far from being as robust as the human visual system or auditory system. Deep networks are known to be vulnerable to carefully crafted imperceptible noise, known as adversarial perturbations or adversarial attacks. These attacks can lead the model to misclassify images to completely unrelated classes. In this example, a 50-step targeted attack is used to flip the image of a prediction of an image from hamster to banjo. Importantly, here we note on the left, the clean, unperturbed image of a hamster is predicted correctly with very high confidence of 99.99%. And with a very minor imperceptible perturbation applied on the right side, we see the perturbed image, and it still misclassifies it as banjo with very high confidence. So this can potentially have disastrous implications in critical applications. For example, hackers could trick a Tesla into accelerating by 50 miles an hour by just attaching a 2-inch piece of tape. A face recognition system can be tricked to predict a different person by wearing a specially designed pair of spectacles. Here we also see that a benign mole is being classified as malignant just by rotating the image by a pre-specified amount. Thus, the compelling need of securing the systems has propelled research in this area over the last few years, and it's been quite intense. Early attempts of improving robustness to adversarial attacks could be broadly classified into input pre-processing-based defenses and adversarial training-based defenses. While the input pre-processing-based defenses were computationally cheap, they primarily involve the masking of gradients to prevent the generation of strong attacks, and thus didn't quite rule out the existence of adversaries within the considered threat model. Several such methods were later shown to be ineffective against adaptive attacks, especially those which are constructed using smooth approximations of non-differentiable components or using expectation over transformations for defenses which use randomized components. On the other hand, adversarial training-based methods largely can be classified into two categories. One is that of single-step defenses, and the second is that of multi-step defenses. Multi-step defenses essentially use a multi-step attack for generating strong adversaries for every image in a mini batch. And canonical examples of these include projected gradient-based adversarial training, which is PGDAT, and trades. And these have essentially been seen to achieve the state of the art in the field for the last few years. However, like one drawback with the multi-step based defenses is that they incur a high computational cost to train. They generally require a large number of forward and backward propagation steps, which is almost an order of magnitude larger than that of standard training. So this naturally inspires work towards defenses that use single-step attacks alone during training. While these come with a much lower computational cost compared to multi-step defenses, they're quite susceptible to gradient masking and lead to this false sense of security. And this is seen even more true when the model is trained for long training schedules and when you increase the model capacity in some sense. So here, for example, we show the loss surface plots of two models, one trained using FGSM adversarial training on the left, and on the right using PGD adversarial training. And you can see that the loss landscape on the left is highly non-smooth with many undulations. And this is a classic example of the model exhibiting gradient masking. So what exactly is this plot? The 0, 0 coordinates essentially depict the clean image, and delta 1 is a direction along the gradient. And delta 2 is a gradient is an orthogonal direction, which is chosen generally to be random, which is also orthogonal to the gradient direction, so that we get a 2D plot. And we see that as we progress along the gradient direction, the loss initially increases, but then it falls back to 0. And this is a classic example of the phenomenon of gradient masking. While robust models, which are truly robust, like PGDAT, are seen to have like smooth loss surfaces, like on the right. Now, with that general introduction done, I'll move on to presenting some of our research in this area. I'll now present our work for evaluating and enhancing adversarial robustness. Namely, the following is matter from our spotlight paper titled Guided Adversarial Attack for Evaluating and Enhancing Adversarial Defenses, which was joint work with my colleagues Shravanti and Arya and Professor Venkatesh Babu at the Indian Institute of Science. This was work which I did towards my bachelor's thesis. So advances in the development of adversarial attacks have been fundamental to the progress of adversarial defense research as well. Efficient and effective attacks are crucial not only for reliable evaluation of these defenses, but also for developing robust models in themselves. On the other hand, robust defenses also motivates research towards developing stronger attacks. For example, several defense-specific adaptive attacks can potentially generalize to other defenses as well, and this has been observed in the field. Therefore, the development of defenses and strong attacks are very closely coupled with each other today. And in this first work, we'll first introduce a novel attack called Gamma, which achieves state-of-the-art results for defense evaluation, and further present a single-step defense, GAT, which uses this attack for adversarial training. The loss surface of deep networks is highly non-convex, due to which a single untargeted attack may fail to find a successful adversary, though it might exist within the constraint set. The use of multiple targeted or untargeted attacks has proved to be effective, but it does come with an increased computational cost. In this work, we propose to utilize supervision from the function mapping of clean samples in order to identify an initial direction that would lead to a stronger attack. We introduce an additional relaxation term corresponding to the squared L2 distance between the probability vectors of the clean image and the perturbed image. The contribution of the L2 smoothing term is linearly decayed to 0 over iterations, so that this term only aids in the optimization process and does not disturb the optimal solution of the true maximum margin objective. Here we show the introduction of a relaxation term does indeed help in smoothing the optimization objective. We consider a simplified one-dimensional example of the maximization of a non-concave biquadratic function, which has a local maximum at x equals -1. Naive optimization using gradient descent or stochastic gradient descent could possibly miss the global maximizer and return this local maximum instead as the optimal solution at the end. By introducing a squared relaxation term, we obtain a family of functions which are more amenable to standard methods of optimization such as SGD. We then linearly decrease the contribution of this smoothing term to 0 over iterations and obtain the global maximizer of the original function at the end of optimization. Here, for example, we show the loss surface plots for an FGSM trained model. In these plots, delta 1 corresponds to the changes along the gradient direction, and delta 2 represents perturbations along a random direction, orthogonal to the gradient, as before. The cross entropy and maximum margin loss plots are not smooth and also exhibit gradient masking, which aligns with our expectations for an FGSM trained model. The third plot, on the other hand, shows the loss surface of the proposed guided adversarial margin attack with the coefficient of this relaxation term set to 25. We find that the L2 relaxation term indeed leads to a significantly smoother loss surface, similar to the one-dimensional example seen earlier. We also find that gradient masking is significantly lower, which is quite helpful in practice. We thus now present the algorithm for the proposed guided adversarial margin attack. The attack is initialized using random Bernoulli noise of magnitude epsilon. This is generally empirically seen to lead to a better initialization when compared to uniform or Gaussian noise, and is seen to result in more reliable gradients initially. At each step, the loss is computed and maximized to find the optimal X tilde for the given iteration. This loss is a combination of the maximum margin loss and the proposed relaxation term, which is the squared L2 distance between the probability vectors of the clean image and the perturbed image. This weighting factor, crucially, of the L2 term is decayed linearly to 0 over the first few iterations. For a 100-step attack, generally, we decrease this to 0 over a period of 25 iterations, and we run it with a lambda of 50. We propose generally two variants of the gamma attack. In the first variant, we use projected gradient descent, or PGD, for the maximization as shown here. And in the second variant, we use Frank-Wolf optimization, which I'll just come to in a moment. The initial step size of the PGD attack is said to be 2 times epsilon and is decayed by a factor of 10 generally at iteration 60 and 85 for a 100-step attack. Finally, the attack is clamped to the valid normalized range for pixel intensities, which is 0 to 1. This process is then repeated for t iterations, and we generally consider 100-step attacks for the values reported in the paper. We also introduce gamma Frank-Wolf, where the optimization is performed using the Frank-Wolf algorithm or conditional gradient descent. This algorithm finds the optimal solution in the constraint set by iteratively updating the current solution as a convex combination of the current point and the point within the constraint set, which maximizes the inner product with the gradient. For the setting of L infinity constraints, this point which maximizes this inner product with the gradient is simply given by the epsilon times the sign of the current gradient. And since the constraint set is convex, this convex combination is guaranteed to lie within the constraint set, and thus this doesn't require reprojection step, crucially. This process is seen to converge faster when compared to PGD, and thus results in stronger attacks when the number of iterations is relatively small. This makes gamma FW particularly useful in the setting of adversarial training, where there is a fixed budget which is frozen ahead of time for attack generation during training. Using the proposed gamma attack, we demonstrate state-of-the-art results across multiple adversarial defenses for both a single run of the attack and with multiple random restarts. So here the initial random noise is varied across the images. Further, we introduce a multi-targeted version of the attack called gamma empty, where the maximum margin loss is replaced by the margin loss directed towards the top 4 classes, excluding the true class. And in the final restart, we maximize the untargeted gamma loss as before. And we see that gamma empty consistently is one of the most effective attacks across all the defenses. We also demonstrate state-of-the-art results across other datasets such as ImageNet and MNIST. In this plot, we show the robust accuracy of a fixed defense against multiple random restarts of different attacks. We find that gamma PGD and gamma FW consistently achieve the strongest attacks while also being less sensitive to random initialization. But importantly, we also note the proposed multi-targeted attack gamma MT outperforms all other attacks significantly on ImageNet, which is particularly better than gamma and is marginally better than gamma PGD and gamma FW on CFAR 10 and MNIST. As we have seen earlier, this proposed L2 relaxation term smoothens the loss surface and results in more reliable gradients initially, and thus yields stronger attacks. This makes it possible and suitable for the generation of adversaries in single-step adversarial training. And based upon this, we propose a single-step defense called guided adversarial training, and I'll present the algorithm here. Initially, we add Bernoulli noise of magnitude alpha to the input image in order to escape any possible gradient masking which might possibly occur in the vicinity of the data sample itself. Next, an attack is generated by maximizing the proposed guided adversarial loss using single-step optimization. And this generated perturbation is then projected onto the epsilon ball just to respect the original constraints which we care about. The generated adversarial examples using this method are then used along with clean samples for adversarial training. We use the proposed L2 relaxation term both for attack generation as well as adversarial training. And we use a cross entropy loss instead of the max margin loss for training, because it's known to be a better objective, especially for training neural networks, while max margin is seen to have issues of its own. And this algorithm is then repeated for a fixed number of iterations, and the best model is chosen using early stopping on a holdout validation set. We also observe that to improve diversity further, we can essentially set this coefficient of lambda in the attack to be 0 in alternate iterations. So this essentially reduces to the simple gradient-based attack using just cross-entropy loss in alternate iterations. And using the technique which I just mentioned, which is called GAT, we present results on the CFAR10 dataset. And the proposed defense is seen to be significantly better than existing single-step defenses, and also scales well to like larger model capacities and large-scale data sets. Further, replacing the inner maximization of trades with the proposed 10-step Frank-Wolf attack, guided attack, in alternate iterations is seen to give a slight boost in adversarial robustness as well. So the proposed gamma FW attack is seen to like slightly improve existing multi-step defenses as well. Also in sharp contrast to other single-step training methods which possibly show gradient masking, we show that the model trained using GAT is smooth, as shown on the right, similar to that of the PGG trained model, which is a multi-step trained model, which doesn't exhibit gradient masking. And this helps kind of verify the absence of gradient masking in some sense in the proposed single-step defense. I'll now move on to discussing another approach which helps increase the efficacy of single-step adversarial training, especially over the previous baseline which I showed, which was guided adversarial training. This was the following is content from our paper titled Towards Efficient and Effective Adversarial Training. And this was again done with my colleagues at the Indian Institute of Science. And this was work which I did towards my master's thesis. I'll give a brief overview of the nuclear norm, nuclear norm regularization using the nuclear norm which we propose to use in this paper. And I'll first give a brief background of its definition and some important properties. For a matrix A, the nuclear norm is defined as the sum of the singular values of the matrix and is denoted as norm A star. It's also equal to the trace of the matrix square root of A star A, where A star is the Hermitian conjugate. And here we can take the matrix square root of A star A essentially because we know that it's going to be positive semi-definite and the matrix square root will exist. Crucially, important property is that the nuclear norm forms the upper bound of the Frobenius norm for any matrix, as we show here. Let A be equal to U lambda V transpose. And we consider this as the singular value decomposition for the matrix A. And crucially, this always exists, unlike, say, the spectral decomposition, which depends on A being a square matrix. So if we look at norm A star square on the left side, we see that it's the sum of the singular values, everything squared. And if we expand the square and multiply out the terms, we first get two terms, one which is the sum of the squares of the singular values. And the second is the sum of cross terms of sigma A, sigma J as shown here. And we use the property that singular values of a matrix are always non-negative. And thus, if we remove it from the sum, we get a lower bound, which is just the sum of the singular values themselves, sum of the squared singular values themselves. And crucially, we see that the sum of the squared singular values is equal to the Frobenius norm of the singular matrix lambda. A nice property of unitary matrices is that if you scale a matrix by a unit, if you multiply it by another unitary matrix such as U and V, the Frobenius norm doesn't change because it keeps, and it essentially just follows from the definition of being unitary in the sense that it preserves vector norms and matrix norms. And as we see here, if we pre-multiply by U and post-multiply by V transpose, we essentially obtain back A. And this essentially helps show that the nuclear norm is a forms a uniform upper bound of the Frobenius norm for any matrix. Also importantly, it turns out the nuclear norm is also provides a tight convex relaxation for the rank of a matrix, and it's the tightest possible convex relaxation for the rank of the matrix. And because it's this tight relation is there, it's often used as a differentiable surrogate objective for rank, because rank itself is not exactly a differentiable objective. We now describe how we can use nuclear norm regularization for single-step adversarial training. For a given mini batch of samples M, let X be the matrix whose rows are the individual images X1 to Xm. And let the corresponding pre-softmax values be represented as the matrix F theta of X. Here, essentially, the pre-softmax values are stacked row-wise to form the matrix F theta of X. And if we further denote the matrix which we obtain from the adversarial perturbations as delta, then the input to the adversarially perturbed mini batch is determined as X plus delta. And the respective pre-softmax values are represented by F theta of X plus delta. Now, we propose to impose a nuclear norm regularization on the difference of the clean and adversarial pre-softmax predictions, which is then coupled with the cross-entropy loss on clean samples to guide the primary classification objective. And the overall loss is shown below, where importantly, the second term is the nuclear norm as defined for the given mini batch of samples. This proposed regularizer not only imposes function smoothing around the data samples, but also imposes a rank minimization constraints on the matrix, like I mentioned just moments earlier. And this helps encourage association between the different columns or classes of the data matrix as well. Furthermore, this allows the samples within the batch to aid each other. And this essentially utilizes the relation between the oscillation of function values across different dimension or classes to obtain a better robustness accuracy trade-off, especially for single-step adversarial training. Here, for example, we visualize the normalized nuclear norm values obtained for different attacks and various defense methods on the CIFAR-10 dataset. Based on the function predictions, we partition images into robust and non-robust sets, just based on the function predictions themselves. And we crucially observe that higher values clearly correspond to the non-robust ones, while the lower nuclear norm values distinctly correspond to robust samples. So this helps validate our hypothesis that explicit minimization of the nuclear norm regularizer can help improve adversarial robustness of the models themselves. I'll now describe how nuclear norm-based adversarial training can help in single-step training in particular. So for a given mini batch of samples, let X denote the matrix of images and let Y denote the corresponding labels. We then randomly initialize the perturbation matrix delta with IID Bernoulli noise of magnitude alpha, similar to before. The following loss is then maximized for the generation of adversaries, where the first term is the cross-entropy loss and the second is the proposed nuclear norm regularizer. Finally, the attack is clamped to be within the considered threat model and to the normalized range of pixel intensities, which is generally 0 to 1, which is the most common setting in some sense. Crucially, maximization of the nuclear norm leads to increase in the singular values of the matrix Fx plus delta minus Fx. And this helps result in more diverse attacks, though it's just a single step attack. The generated adversarial attacks are encouraged to go to a diverse set of classes as opposed to the most confused class alone, which is the most common target in standard cross-entropy based attacks or in attacks which utilize the Frobenius norm. Indeed, here we verify the same. We compare the confusion matrices for predictions of a normally trained model on the CIFAR-10 dataset against adversarial attacks generated by maximizing the nuclear norm and Frobenius norm, respectively. It can be observed that the nuclear norm attack results in a better diversification of the target classes after attack when compared to the Frobenius norm attack. It can also be observed from the diagonal entries of the confusion matrix that the nuclear norm maximization results in a stronger attack when compared to the Frobenius norm attack. I'll now present the overall algorithm for the proposed single-step training scheme called nuclear norm adversarial training, or NUAT. We first generate the adversaries by maximizing the nuclear norm regularizer in addition to the standard cross-entropy loss by using a single gradient update. In the adversarial training step, we minimize the nuclear norm of the matrix, consisting of the same difference of pre-softmax values for the clean and perturbed images, in addition to the cross-entropy loss. And crucially, we use this both in the attack generation as well as the training step. We increase this value of lambda linearly over training epochs to achieve a better clean accuracy. And we further set the coefficient of the nuclear norm regularizer term in the attack step to 0 in alternate iterations, similar to before, to improve attack diversity even more over the baseline. While the nuclear norm attack encourages the generation of diverse perturbations by virtue of maximizing nuclear norm, by virtue of maximizing singular values, the NuAT defense attempts to minimize the same, preventing over-smoothing of the loss surface uniformly in all directions, which would have been the case in Frobenius norm training. And this helps lead to a better robustness accuracy trade-off as well. And finally, this overall algorithm is repeated for a fixed number of epochs. And similar to before, we use early stopping on a holdout validation set. I'll also present a variant called NuAT2, where we use 2 steps for attack generation. In the first step, we maximize the nuclear norm regularizer-based loss, similar to earlier, similar to the single-step attack. Whereas in the second step, we use only the cross-entropy loss, which corresponds to setting the value of lambda to 0 in the same attack. So the use of the nuclear norm relaxation in the first step helps in generating more reliable gradient directions by smoothing the loss surface. And the cross-entropy objective in the second step is optimal for fooling the classifier itself. In contrast to the standard PGD 2-step training, we also use the step size of epsilon for both these steps in order to allow the best of both objectives to drive the generation of the final attack, which we use for training. And here I'll introduce something called hybrid adversarial training. So it's been observed in prior works that single-step defenses cannot really be used for very long training regimes due to issues related to stability, which is seen during training itself. And while the proposed NuAT defense, single-step defense, is significantly more stable compared to prior works, it's not exactly as stable as the 2-step defense NuAT2 for large model capacities and training schemes. As shown here in the figure, the onset of gradient masking is often accompanied by a sudden drop in training loss. And motivated by Lee et al., we compare the current loss on clean samples with the average loss of the previous epoch. And we use this to adaptively switch between the proposed single-step and 2-step attacks so that we improve on the computational complexity required. When there is a sudden drop in the loss, we switch to a 2-step attack momentarily. And we switch back to the 1-step attack once the loss curve recovers. And this is often seen to be highly effective. While prior works often require a separate validation set and use 10-step based training for stabilizing the model once a failure mode is seen. Here we quite seamlessly switch between our single-step and 2-step training methods without any real additional overheads. And we obtain significantly more robust and stable models compared to the single-step training alone, while requiring an additional overhead of only 5 training epochs. And this is seen to be particularly effective for large model capacities, such as wide ResNet in particular. So I'll now present some experimental evaluations for the proposed method and evaluations on strong attacks, such as auto attack. Here we present results on the CFAT and dataset for models trained using the ResNet 18 architecture. We observed that the proposed method NuAT performs significantly better than existing single-step training methods, as shown in the first partition of the table. Further, we note that despite using only single-step adversaries during training, NuAT performs better than multi-step defenses such as PGD and trades on the ResNet 18 model. We further observe that by incorporating exponential weight averaging with the proposed single-step defense, which is denoted as NuAT1, where we maintain an exponential running average of the weights during training, we achieve enhanced robust performance along with higher clean accuracy as well simultaneously. And NuAT was seen to significantly outperform other methods with weight averaging included compared to the previous baseline of GAT-VA, and even trades VA for the ResNet 18 model, and in fact achieves robust accuracy comparable to that of adversarial weight perturbation in the last row here. Here, we present results on the CIFAR10 dataset again, but using the wide ResNet 3410 architecture. We note that NuAT significantly outperforms the baseline given by fast is better than free, which is denoted as FBF in the first row. Since FBF suffers from catastrophic overfitting on these larger model capacities such as wide ResNet, we also remark that NuAT achieves better robustness and is able to strike a more favorable robustness accuracy trade-off as compared to GAT for the reasons mentioned earlier, while requiring far few epochs for training as well. For example, here we only require 55 epochs for NuAT, while others such as GAT use 85. Next, we observe that the two-step nuclear norm adversarial training, or NuAT2, achieves significant gains in robust accuracy compared to NuAT as well, especially so with the weight average model NuAT2-WA. Next, we also observe that the hybrid-based training with NuAT effectively bridges the complexity gap between NuAT and NuAT2, while requiring an additional overhead of only 6 training epochs, where the two-step adversaries are used for attack generation. And we observe that the difference in robust performance is quite minor between that of the hybrid train model and the NuAT Part 2, which genuinely uses 2 steps for every epoch of training. And here we present some consolidated results across 3 standard data sets, CIFAR10, ImageNet 100, and MNIST, against some of the strongest known white box attacks, including Gamma and Auto Attack. And we observe consistent improvements in robust accuracy compared to even multi-step defenses while maintaining high clean accuracy. For example, on ImageNet 100, the model with weight averaging is seen to achieve about 33% accuracy, auto attack accuracy, which is quite significantly higher than that of trades and PGD80, while also achieving quite good clean accuracy simultaneously. So here we demonstrate the computational complexity of the proposed algorithm with various other defenses as well on the wide ResNet 3410 architecture on the CIFAR10 dataset against auto attack. We observe that the proposed single-step defense NuAT and hybrid NuAT achieve significant improvements in robust performance over other single-step methods while maintaining quite a low computational budget. Furthermore, the proposed NuAT WAT2, the two-step defense, achieves a robust accuracy of 54.76, and it outperforms other multi-step defenses, including trades and PGD, as seen in the plot here, while requiring a significantly lower computational cost, as seen in the X coordinate. I'll now move on to how we can essentially implement these single-step techniques for training robust models that are valid across multiple different threat models simultaneously. So namely, this is the following will be content from a paper titled Toward Efficient Robust Training Against Union of LP Threat Models. And this was joint work with my colleagues, Maharshi Gore and Professor Sohail Faizi at the University of Maryland, College Park. So the goal of an adversary is to alter a clean input image such that the attacked image is perceptually similar, true, but causes the network to misclassify in general. And diverse operational frameworks have been developed to quantify perceptual similarity, especially for this. And adversarial attacks corresponding to several of these constraints have been studied extensively in the past. And while the primary focus of existing approaches has been directed towards addressing the worst case performance under a single threat model, human imperceptible noises can often be sourced from multiple threat models in practice. And a natural generalization which we can ask for is whether a robust model can generalize across different LP norm threat models since it's well characterized. And recently, there's been even some work for LP norm threat models for P less than 1. And these LP norm spaces are not exactly norms when P is less than 1. And as you can see, the unit balls are shown here. And when P is less than 1, we get non-convex balls. So the standard unit balls are no longer convex if P is less than 1. And diverse adversarial analysis have been extended even for P less than 1. But we'll essentially focus on the most popular variants of LP norm threat models, which is the L1 threat model, L2 and L infinity, with particular emphasis on L1 and L infinity, as we'll see. So what do these different threat models look like in practice? So let's visualize some of these for the different threat models. As before, here we have a L infinity based PGD attack, which is generally the standard which is followed, for an attack budget of 8 by 255, which is generally the standard. And the perturbation shown in the middle has been scaled up in magnitude by 50x, just so that it's perceptible and you can see the patterns involved. And we get the image on the right. Crucially, we see that every pixel in the perturbation is has a non-zero value in some sense, and that every pixel of the original image gets perturbed in these L infinity attacks, and thus we get a dense perturbation. On the other hand, here we show an example of an L2 based attack with an attack budget of 0.5. And we kind of see that how the L2 based attack focuses a lot of its available budget on like several pixels, which are spread thin over the entire image. And this is quite a sharp contrast to that of L infinity attacks, where it's dense over all pixels. And here we show an example of an L1 based PGD attack with an attack budget of epsilon 17. We again note how the L1 based attack focuses much of its available budget on very few pixels across the entire image. And it's a lot more sparse than the L2 based attack, and is significantly more sparse than the L infinity based attack. And for this reason, the L1 attack is often used to model sparse attacks in the same way that L1 norm is often used to is often used as a approximation of L0 or the counting norm. It's not exactly a norm, but for the counting metric in some sense. Where only a few pixels are allowed to be perturbed in the original sample. So what are some of the challenges involved in robust training in this setting for the union of threat models? So largely to achieve robustness under this union of threat models, prior works either use a large number of attack steps for different adversaries. Namely, one a simple approach might possibly be to use multi-step attacks for each threat model. So say you have L1, L2, and L infinity. You can possibly generate 10-step adversarial attacks for each of these threat models and minimize the loss achieved by adversaries, by any of these three adversaries, by the maximum of these three adversaries, or even the average of these three losses. And this was what was used in past works. There was also an approach called a maximum steepest descent, which is shown in the animation on the right, which is taken from this paper, Adversarial Robustness Against the Union of Multiple Threat Models, which was an ICML 2020 paper, where they essentially generate a perturbation across all three threat models and essentially keep only the final perturbation for the current iteration, which maximizes the loss. And the other distinct approach has essentially been to fine-tune existing robust models, but these essentially rely on the existence of models that are already robust against a single threat model. And we essentially want to extend this to an efficient setting so that it can be carried out in practice more effectively. And another important problem which we see that is that L infinity robust models are often seen to be vulnerable against L1 attacks and vice versa. So if a model is trained to be robust only against L infinity, the robustness doesn't quite transfer over to L1. And the same is seen for L1 trained models being non-robust to L infinity based attacks. And crucially for L1 based training in particular, even some multi-step adversarial training methods are seen to be susceptible to catastrophic failure just because of how sparse these L1 attacks are. And I'll go into some more detail in the following slides. This partly arises due to the fact that the geometry for L1 and L infinity based adversaries is very different, and the optimization inherently is different. For example, if you consider steepest ascent with L infinity based constraints, it often involves taking the sign of the gradient, just like in FGSM and other related iterated variants like PGD or IFGSM. Whereas let's look at steepest ascent in L1 geometry. So what do we need to do? We want to maximize the inner product with the gradients GI here. And we want to maximize we want to find the perturbation delta, which maximizes the inner product, such that the final image lies within image constraints as before, and that the perturbation has a limited L1 norm, which is depicted as epsilon 1 here. And it turns out that it's fairly easy to show that steepest ascent in L1 essentially involves selecting the gradient component with the largest absolute magnitude and entirely saturating that particular pixel up to image constraints, which is 0, 1 in our case. And this process is essentially repeated iteratively in a descending sorted order of the gradient component magnitudes till the L1 budget is utilized. So what do we essentially do? We compute the gradient, which isn't quite restricted in some sense. We sort them by the absolute value, and then perturb the pixels up to image constraints as possible till we utilize the entire budget. And due to this particular fact, the L1 perturbations which are generated in this sense are usually very, very sparse because of this particular fact. And this often complicates adversarial training in the sense that it makes training very prone to catastrophic failure and extreme overfitting in some sense, where the model just simply learns to memorize adversaries rather than becoming truly adversarially robust. And given these complexities, we again try to hypothesize that instead of minimizing point-wise adversarial losses, enforcing function smoothing is much more pertinent and effective in practice. And since we have the overall goal of achieving this in an efficient framework, we want to use single-step adversarial training, and thus we propose to use nuclear norm regularization. So let's see what happens when we use this. So it turns out that single-step defenses in particular are highly non-robust in the L1 setting. So for example, here we denote the L1 validation accuracy and validation cross-entropy loss curves for a couple of models. Namely, we see that standard RFGSM or fastest better than free based training, which uses FGSM adversaries, is quite non-robust in the sense that we observe failure fairly early. And in contrast to that of L infinity, particularly for the case of L1, we see that even nuclear norm adversarial training is not quite stable enough for resonant 18 based training for even 100 epochs. And this essentially results in suboptimal robustness for L1. While essentially the only state-of-the-art methods available for L1 use multi-step adversarial training. So a priori, it might appear that single-step methods might not be quite effective or useful at all. However, like to rectify this situation, we try to propose a curriculum schedule to select the nature of these L1 perturbations during training. We essentially find that different curricula are effective in practice, including those that incorporate the robust accuracy on training samples observed at a given epoch to dynamically vary the perturbation budget at different rates. So using this method, we essentially ensure that the model learns on simpler adversaries at the start of training and more difficult adversaries as training progresses. However, we kind of observe that for these complex curricula, they essentially require additional fine-tuning of hyperparameters, which is not really great. And we also find that these values are sensitive to the particular threat model which is used, say L1, or even if you use it for L infinity, these values seem to change quite a bit and result in suboptimal values of robustness if not tuned correctly. We thus quite utilize a simple linear schedule where the perturbation size is linearly increased from 0 to epsilon, and it's kept constant for the last few epochs alone. To facilitate adequate fine-tuned training on the final threat model of interest, which is generally, say, for example, L1 a perturbation budget of 12 on CIFAR 10. To also achieve robustness against a union of threat models, we propose to use a decision function to select the adversary generation. And this is in quite sharp contrast to that of prior works that use multi-step attacks across different threat models. Using the proposed decision function in this case, we maintain a low compute requirement of just using a single step attack per mini batch. Thus, what we essentially find in practice is that a predefined frequency or probability for choosing these adversaries is good enough. And it doesn't quite have to dynamically vary over the training procedure as well. And we essentially observe that using these proposed changes, we observe that the proposed L1 method, nuclear norm curriculum adversarial training, which we shorten as NCAT, is seen to be stable throughout the training regime and achieves enhanced robustness. In fact, we observe that even if training is continued for later epochs, it only saturates, and we don't observe sharp failure modes, which are seen in other single-step methods. And indeed, the proposed method NCAT, we first present results on Resident 18 on CIFAR 10. And it seemed to achieve a high degree of robustness, both for L1 adversaries alone, which is shown in the first partition, and also under the union of these LP threat models in the lower partition. Interestingly, we also find that the single-step NCAT L1 train model in the first partition for the L1 model alone generalizes and achieves a higher degree of robustness against unseen threat models such as L infinity and L2, as compared to the multi-step L1 defense APGD L1. And when we allow training under the union of threat models using the proposed decision function, we also obtain fairly comparable values of robustness as seen for both the worst case setting and average case setting, while using only a fraction of the computational cost as we can see here from the number of adversarial training steps which are available for each mini batch. And it's worthy of mention that prior methods essentially rely on multi-step attacks across multiple threat models, which is why for this setting of achieving robustness across for the union of threat models, we generally find other defenses using a large number of steps such as 30, 50, or on average 13.33, just due to the fact that we have multiple threat models in this scenario. And we also verify that the method scales well to stable training on larger networks such as wide ResNet, where we observe that similar trends continue to hold true. Despite using only a fraction of the computational cost, which is even more worthy of emphasis for training wide ResNet networks as compared to the standard ResNet 18 networks, for example. We also present results on ImageNet 100, where we importantly note that the NCAT defense achieves a high degree of robustness even against the perceptual projected gradient descent attack, which is one of the strongest attacks known to date. So this is essentially a generalized adversarial threat model, which is not an LP threat model, which essentially relies upon the LPIPS distance of a pre-trained robust network to essentially decide how far two images are. And this essentially is shown to correlate well with human perception as well. And this has been known to be one of the strongest attacks known to date. And we see that the proposed defense generalizes to this attack as well, though it's not been trained explicitly at all on these. So in summary, I had essentially presented three primary approaches. First was guided adversarial optimization, where we utilized a graduated optimization scheme using a surrogate loss term, which was linearly decayed to 0 over iterations, so that the overall objective is robustified. Using this, we propose a attack called guided adversarial margin attack, or GAMA, and this helps in establishing enhanced worst case evaluation for a low attack budget. Using the same, we also obtain reliable single step training and guided adversarial training. Building upon this, we propose to use nuclear norm regularization to create an efficient scheme for single step adversarial training, which is more effective in practice. To do so, we utilize batch statistics entirely to improve efficacy of single step training. And we essentially observe extensions to hybrid and two-step defenses, which almost achieve the same results as multi-step defenses if we are allowed a minor increase in the computational budget for training. Lastly, we see the generalization to multiple threat models and how we can achieve the same using single-step attacks alone. Namely, we use a curriculum schedule to stabilize L1 training first, and then we use a decision function to help generalize over multiple threat models simultaneously. And we do this using only a single step attack for each mini batch. So I hope the presentation was interesting, and I'd like to thank the organizers for inviting me for this talk as well. And if there are any questions in the audience, I'd like to take it.
Thank you very much for your great talk. I have questions.
Sure.
For the L1 adversarial training, your experiments show that nuclear norm regularization doesn't work in some sense, in some point. there is a catastrophic overfitting. Then you have to use a curriculum learning strategy to make it stable. My question is why nuclear norm organization doesn't work in L1 training?
So largely, we kind of observe that this is just due to the fact that L1 training in particular is much more difficult than L-infinity training, usually, especially for the constraint threats, which we consider, which is like 12. So for example, if you consider a small L1 budgets of say 4, like standard new 80 would work well. And the difficulty essentially comes with the fact that the L1 budget which we work with is generally large for the constraint threats. And this is particularly worthy of mention because like prior methods, multi-step defenses which use like the slide attack, for example, they are multi-step defenses, yet they also are seen to suffer from the same catastrophic overfitting in some sense. And this is essentially because the L1 attacks are very sparse, and the network during adversarial training essentially overfits to the L1 perturbations alone, rather than becoming like truly robust in some sense. And this essentially breaks the model at some point during optimization. Yeah.
I see. Then the curriculum learning helps in this part. Then the following up question comes: would the curriculum learning help in single step L-infinite adversarial training, like the fast adversarial training? This is the very first method.
So we do essentially observe even on L-infinity that say for 8x255, you may not quite need the curriculum schedule. But if you're training on much larger epsilons, like say 16x255, which is generally the larger, largest values of epsilon, which makes sense on these standard data sets like CIFAR-10, curriculum scheduling does indeed help. So if you linearly increase the epsilon up to 16 and like plateau it for the last few epochs, it'll certainly help for these larger L-infinity based training as well for single step.
I see. Therefore, could I conclude that no matter what kind of training, L1 training, L-infinity training, L2 training, would the curriculum learning strategy will help all training strategies? It won't hurt.
So in general, it doesn't quite hurt, especially for these smaller epsilon values. Rather, I guess it becomes a question of additional hyperparameter about like for how many epochs do you linearly increase it and so on. And you might get away without the use of this hyperparameter. But yes, indeed, in general, it's quite effective.
I see. Then we can, in practice, we can just apply the curriculum learning.
Yeah, exactly.
Without bothering there are some side effects. Got it. Okay. Thanks for a great talk. Hi, audience. If you have any questions, you can open your mic to talk, and also you can type it in the chat box. Then maybe there are no further questions. Maybe they can email you if they are later read your paper and they want to ask you. Okay. This is the end of today's seminar. Thank you very much for your great talk. We are really happy to have you.
Thank you so much for inviting me for the talk as well. It's quite a privilege to speak at this venue. Thank you.
Thank you. Then bye-bye.